This lecture is devoted to the stability theorem, which is the second or first most important theorem in the story of persistent homology. It plays a very different role from the structure theorem, which allowed us to decompose any tame persistence module into its barcode. It plays a geometric role. Its purpose is to be able to sort of confer some geometric rigidity to the space of persistence modules, which, as we know from the last lecture, forms a metric space under the interleaving distance. So to state the stability theorem, we need a notion of distance between barcodes, which is much, much easier than the interleaving distance, because barcodes are much simpler looking objects than persistence modules. So let B and B prime be two barcodes. And I want to think of these as sort of divorced from any persistence module. So by barcode here, I just mean finite sets of intervals, let's say ST, living in R, possibly allowing for T to be infinity, with some multiplicities. So each of them might occur. It's not, what I want to say is each ST could occur 5 times or 12 times or something like that. So it's not a unique element like you would have in a set. So the way we define the interleaving distance between persistence modules was to construct an interleaving and then take an infimum over all available interleavings. And so something similar happens in the case of barcodes, but again, the object to construct is much simpler. So here is the object that allows us to compare B and B prime. And epsilon matching, and I say this for some epsilon bigger than or equal to 0, between B and B prime is a bijection, which I'll write as, say, gamma from B0 to B0 prime. So this is going to be between subsets B0 of B and B0 prime of B prime. So it's a pairing, a one-to-one and onto map. So it's pairing some intervals in B0 with some intervals in B, which we call B0, with some intervals in B prime. That the things that get matched by gamma are called B0 and B0 prime. And this is subject to 2 constraints. So far, no epsilon has entered the picture, so obviously we need a little bit more. So the first constraint is what happens to the intervals that don't get matched. Every interval in B minus B0 and in B prime minus B0 prime has length less than or equal to 2 epsilon. So none of the intervals that are unmatched by gamma in the bijection can be very long relative to epsilon. So one thing this already implies is that none of the infinite length bars can be unpaired if an epsilon matching exists. And the second part is how close things are that get matched. So if gamma of some interval st in B0 is S prime T prime, so if these two get paired together, then the distance between S and S prime, the first endpoints, and the distance between T and T prime, the last endpoints, both these distances can be no longer than epsilon. So if you like pictorially, here's the real line. Here is some S, here is some T, and of course, emotionally, we always allow T to be equal to infinity, so that point may just be all the way off to the side. And so here is, between S and T, is the interval that we're trying to match. And this constraint just says that S prime can live no more than epsilon away from S, and similarly T prime can live no more than epsilon away from t. So you get s prime t prime from st by wiggling the endpoints by epsilon. And if you think about this in the sense of wiggling by epsilon, this explains the first bit, why the intervals that are unmatched have to have length less than or equal to 2 epsilon. If s and t were within 2 epsilon of each other, you could wiggle s to the right and wiggle t to the left, and poof, the whole interval would vanish. So this is the definition of an epsilon matching, and sort of unsurprisingly, the bottleneck distance, that's what the metric is called in the space of barcodes. So the bottleneck distance between B and B prime is the smallest epsilon bigger than 0 for which an epsilon matching exists. So matchings are playing the role of interleavings. And again, I think these are much simpler. There's no algebra. There's just, direct combinatorics matching intervals to intervals. I guess the thing to watch out for is that when intervals occur with multiplicity, so if the interval, 2.8 has occurred 3 times in B, then you have to match it with either 3 different things or have an epsilon interleaving that's, less than half the length or something like that of that interval that you're leaving unmatched, a matching rather than an interleaving. Okay, so that's the whole definition, and we're all ready to state the stability theorem. So here it is. So stability. Whenever you have, so for any pair V and W of tame persistence modules, we have an equality. So the interleaving distance, as defined in the previous lecture, between V and W is equal to the bottleneck distance of their barcodes, which are guaranteed to exist by the structure theorem. So this is sort of absolutely amazing. If you think about how the interleaving distance is defined, it's defined in terms of all these strange algebraic braiding relations between one parameter families of vector spaces. And you think about how the bottleneck distance is defined in terms of matching these bars that occur when you decompose these these families of vector spaces, these persistence modules, into the simple indecomposable types, which are just the interval modules. It's absolutely amazing that this process that factors through the classification of finitely generated FT modules would respect any sort of geometric structure at all, and yet here is the theorem. So that's the good news. The bad news is that the proof of all proofs that I know of this theorem are sort of too complicated to be involved to be mentioned here. But there is a 2015 paper called the Induced Matchings and Algebraic Stability something. So this is a paper circa 2015 or so by Lesnick and Bauer, or Bauer and Lesnick is how I should have said that. And so you can go here, and it's fairly readable, but it still takes them about 30 pages to prove this, and I absolutely will not be going through anything like that in the duration of the sort of video lecture. But it's not a bad read. It's fairly elementary. It just takes a lot of technical stuff to set up. Okay, so instead of dwelling on the proof, which is sort of annoying, let me talk about what this theorem is good for. And this is sort of the big picture of topological data analysis. This is the one image which will explain why we went through all of this trouble of talking about homology, functoriality, simplicial complexes, going all the way back to the first week of the course. So the starting point of topological data analysis is some data set. So you start with your data, which I guess we can think of as some points in Rn. Now, from this data, we've seen ever since the first week of this course that we can build a family of filtered simplicial complexes using either the Vietoris-Rips filtration or the Čech filtration. I don't care which. Let's just say Vietoris-Rips. So you start with the points, and then you sort of start throwing in edges, and then you start throwing in triangles, and so on. And so as this scale parameter t increases, you get a filtered simplicial complex indexed by t. So filtered simplicial complex. Now, once you have a filtered simplicial complex, you can apply homology in any degree you like, the first homology, zeroth homology, etc. And if you did all of them, then you'd get persistent homology. So in dimension 0, you'd get the zero-dimensional persistence module. Here you would get the one-dimensional persistence module. Here you would get the two-dimensional persistence module. And what you should think of is that the scale t, which was indexing the Vietoris-Rips complex, is still the same t that's indexing the persistence modules. And if you, for instance, went there, that spot is the first homology group of the Vietoris-Rips complex at scale t around p. And of course, as you move t to the right, there are inclusion maps, and those maps give you the sort of tame persistence module. So far, we're talking about sort of purely algebraic topological stuff. And then here, the new thing that we've seen is that you can take barcodes for each of these modules. And what that's going to do is it's going to produce these multi-sets of intervals of the kind that we've been discussing. So in dimension 0, you could have these bars with some birth and death. In dimension 1, you could have some of these bars, and so on. So this is going to be barcodes. Let's call them bar sub k of p. So if I was being honest, I would write this as bar sub k of h. Sorry, bar sub k of the bar kp should be bar of hk of vrt of p, but that's entirely too much. So this is just the kth homology barcode. Okay, and now because these barcodes are just finite lists of intervals, maybe with some multiplicity in the worst case, but finite information, you can feed them into all sorts of statistical inference frameworks. The current sort of champion is our neural network. So you could feed them as vectors because they're already so nice and combinatorial. You could linearize them and feed them into some nice neural network via vectorization, so just a feature map. And so you land up in some neural network. And this is the pipeline. So if you had some training data on the upper left corner of this figure, you could see what the feature maps looked like, and then you can use the information that you get from training to predict or classify that data. So this is the topological data analysis pipeline. And what's the point of the stability theorem? Well, the stability theorem makes this entire pipeline robust to noise. What I mean by that is if you took your original data set and perturbed it, then going all the way around, at least up until the feature map stage, you would be able to quantify the change. So if the red points on the left, the new noisy ones that I've introduced, were within epsilon of the gray points that we started with, then if you rolled all the way around to the barcodes, the bars would only change in their endpoints by 2 epsilon. So that's the result. So I'm going to explain why that's the case, but But what you should keep in mind is that this entire pipeline up to the barcodes is stable to the sorts of bounded epsilon noise that you might have in your data measurements. And so this is why the stability theorem is great. It gives you this sort of confidence that at least the long bars, the ones whose endpoints are more than 2 epsilon away from each other, cannot possibly disappear if you make a tiny epsilon perturbation. So the key to this, why this works, is the following proposition combined with the stability theorem. So let P and Q in Rn be finite point sets that are epsilon closed in the following sense. If you thicken P by epsilon, then you contain Q, and if you thicken Q by epsilon, you contain P. So another fancy way of saying this, and maybe we should say it explicitly, just to make sure we're all on the same page about what's going on. The fancy way of saying this, of course, is for every P in P, there exists Q in Q, so that the distance P minus Q, the Euclidean distance, is no more than epsilon. And similarly for Q. In Q, there exists P in P such that distance. And now, I'm not saying that this is a one-to-one matching. This property can be satisfied if P has 4 billion points and Q has 7 points, as long as those 4 billion points are very near the 7 points of Q. So this is still part of the hypothesis. So we have these two nearby point clouds that satisfy this epsilon thickening containment closeness. Then for every homological dimension, so k bigger than 0, the Vietoris-Rips homology persistence modules, or so let's say Vietoris-Rips persistent homology modules, let's write them as HK VRT of P and HK VRT of Q. These are, of course, defined for all t bigger than 0. So these are 2 epsilon interleaved. And because they're 2 epsilon interleaved, you use the stability theorem up here to say that the persistence modules on the right of the screen for P are going to be epsilon interleaved with the ones for Q, and therefore the barcodes are going to be matching distance epsilon from each other, because the stability theorem gives us this lovely isometry between interleaving distance of persistence modules on one side and the bottleneck distance between their barcodes on the other side. So that's sort of the big deal. And let's see, how would you go about proving this? So I've written it out nicely in the notes, so this is going to be more of a sketch. So let's see, by the epsilon closeness of P and Q, there exist functions. So let's call them alpha going from P to Q and beta going from Q to P, such that alpha of P, the distance between alpha of P and P is less than epsilon, and the distance between beta of Q and Q is less than epsilon, and this first thing is for every P, and this is for every Q. So this is just a rephrasing of the epsilon closeness condition. Good. So what happens is you sort of have to think about what alpha is giving you. So there's a very similar story for beta, but I'm just going to focus on the alpha side for now, and then you can symmetrically develop everything I'm saying for beta. So the claim is that alpha induces a simplicial map let's call it alpha sub t, between the tth Vietoris-Rips complex of P and the T plus 2 epsilon Vietoris-Rips complex of Q. And if you want to know why, so let's figure that out. This is because if you took a simplex P0 PK in VRTP, that means if you took any one of these any two of these k plus 1 points, P0 through PK, and you measured their distance, that will be no more than t. But that means that if you take alpha of P0, alpha of PK, by the triangle inequality, so each alpha image of a P is within epsilon of that P, and any two P's are within T of each other. So the alpha images must be within 2 epsilon of each other. So this is silly triangle inequality nonsense. So T plus 2 epsilon Q. So this is the reason alpha T is a simplicial map. And what's nice, because we're defining, the T dependence isn't really huge. So if you include VRS into VRT for all S less than T, and then you take this alpha S, which sends you to 2 epsilon, and then you include that into T plus 2 epsilon, this entire thing commutes. This is just by the definition. I mean, you can chase this simplex by simplex. It's not going to matter whether you go, you take a simplex in BRS, but you push it right, include it to itself, and then hit it with alpha T, or you do alpha S first and then include it. It's going to give you exactly the same thing, which is the alpha images of the vertices. So, so this commuting diagram is on the level of simplicial maps. So when you take the kth homology, it continues to commute by the functoriality of homology. So this is why we wasted / spent so much time developing the functoriality of homology. So it still commutes when we apply HK. So what this is saying is that the set of maps HK alpha T, or T bigger than equal to 0, satisfy the parallelogram relation required by a 2 epsilon interleaving. So let me remind you that HK alpha T are the maps on simplicial homology induced by these simplicial maps alpha T. So we have we've satisfied, basically, if you forget the beta story, which is entirely symmetric, so you can replace alpha with beta at P points with Q points and get a similar commuting diagram. So the two parallelogram laws are easily satisfied. So so HK alpha T is our candidate for the phi sub T maps, the half of the interleaving data that we need. The harder stuff is going to be the triangle relations. So remember, that requires us to show that for all t greater than 0, we need to show that if you had some homology in VRT of P, and then you used HK alpha T to get you to the kth homology of VRT plus 2 epsilon Q, and then you went up to VRT plus 4 epsilon, I suppose, and then this map was induced by inclusion, that this commutes. And we're going to prove this by retreating to a very sort of to something we saw many weeks ago. So this is about a month ago now, something we saw in the second week. So let's see why this is true, why this triangle commutes for every t. So here's the scenario. We go back to the simplicial level. So for sigma equal to, let's say, the same simplex where you talk about P0, Pk in VRTP. So on the one hand, the inclusion map, the horizontal map that's taking you to t plus 4 epsilon is going to send sigma to sigma. So that's easy. We want to know what happens when you go down by alpha and then up by beta. So let's just apply the simplicial maps. Now, what happens is alpha of sigma is going to be alpha P0, alpha Pk. We've already talked about this, living in VR t plus 2 epsilon q. When you apply beta to it, then you get beta alpha of P0, beta alpha of Pk in VR t plus 4 epsilon of P. So we're back in the upper right bit of the triangle that we want to show commutes. And so the inclusion maps send sigma to sigma, and our composite map sends sigma to this beta alpha of vertices. And all you have to know is that sigma union beta compose alpha sigma is also a simplex in VR t plus 4 epsilon p. And this is by the triangle inequality. So if you take any vertex of sigma, which is P0 through Pk, and compare the distance between two of them, you're guaranteed to be within t plus 4 epsilon. In fact, you're guaranteed to be within t. If you take any pair of vertices here, you're guaranteed to be within t plus 4 epsilon. And now if you want to compare, let's say, P0 to beta alpha of Pk, you realize that the distance between P0 and Pk is at most t, and the distance between Pk and beta alpha of Pk is at most 4 epsilon, because alpha gets you 2 epsilon away, and then beta gets you epsilon away. So it's at most 2 epsilon, I think. So if you look at all of these vertices here, P0 through Pk, and then look at all these vertices here, beta alpha P0 through beta alpha Pk, none of them can be more than t plus 4 epsilon apart. And therefore, the two simplicial maps, so the inclusion and beta alpha, are contiguous simplicial maps. And we saw this as way back when as the application of the carrier lemma, that they must be homotopic. And because homology is a homotopy invariant, they induce the same map on homology. The same map on kth homology for all k. So if you go back up to the triangle, all that's saying is that beta composed with alpha is it's the same map on homology as the inclusion of the torus-Rips complexes on the kth homology. And so that's it. That's the proof that the triangle relation holds. And there's a similar story where you do beta first and then alpha, and then end up taking in Q, the Vietoris-Rips complex Q. Again, that's an entirely symmetric argument. So this is why we defined interleavings the way we did as these braidings. It's because when you choose these nearby points, beta composed with alpha is not guaranteed to exactly be the identity, but you can always find something in t plus 4 epsilon that's homotopic to just having included the Vietoris-Rips complex. So if you understand this argument, great. If you don't understand this argument, either watch the video again or go read through the lecture notes where things are written sort of more painstakingly, and then go back to the definition of interleaving and see why the two laws are the way they are, the parallelogram laws and the triangle laws. Anyway, that's it for now. Next week, we see cellular sheaves, which are very exciting indeed. So catch you on the other side.